It has been requested that before we get into the next section of this class, we do a brief review of hypothesis testing means and sort of back up a little bit. So that seemed reasonable. So let's start with some basic facts. The mean is the average score. Not everyone has the same score. And the average amount by which people differ from the mean is the standard deviation. Okay? Just basic descriptive statistics. So let's meet Maria and Eric. And Maria and Eric are going to meet some z-scores. Let's use them for an example to look at when to reject the null hypothesis. If z is small, low probability means it's not likely to occur. So you reject it, right? No, that's wrong. If p is greater than 0.86, and when you have a large z-score, you reject the null hypothesis. So if p equals 0.86, you reject it, right? No, that is also wrong. So let's clear these up. First question, is Eric abnormally tall? Eric is 6 feet 4 inches tall, or 76 inches. That is a high number, both in mathematical terms and off the ground high. What I want to determine is if Eric's height is significantly different from the mean. So I'm going to compute a z-score. Remember, we talked about this in class. Z is the obtained value, in this case 76 inches, minus the population mean divided by the standard deviation. One way to get the mean and standard deviation here is I use SAS, so I did proc sort, which not surprisingly sorts the data. Data equals, I used the SAS help dataset, which has a bunch of heights, so I did SAS help.height. Out equals temp, so I created a temporary dataset that was sorted by sex. So that's how you do a proc sort. Sort your dataset. There you go, by sex. And this out equals is going to create another dataset that is the sorted version of the original dataset. So now I'm going to do a proc univariate, which gives me univariate statistics on that. So proc univariate, data equals temp, var height, because the only variable in the dataset I want the univariate statistics for is height, by sex, because I want them for males and females separately. All right, so I look at those results, and I find that the mean height for the large number of men in that heart study is 67.6 inches, and the standard deviation is 2.7. So I'm going to take that as my population standard deviation and mean. So then I compute my z-score, which is the obtained value of 76 inches, minus the mean value of 67.6, divided by the standard deviation of 2.7. This gives me a z-score of 3.1, which tells me that Eric is 3.1 standard deviations above the mean. Now, what does that tell me? In other words, Eric differs from the mean over 3 times as much as the average person. So, there is a very small probability of large differences from the mean. A score of 1.96 occurs less than 5% of the time. That is about 2 standard deviations from the mean. So 95% of the time, people are within 2 standard deviations of a mean. How often does a z-score of 3.1 occur? Well, the probability of that, if we looked it up in a z-table, would be less than 0.002, so less than 2 times per 1,000. So even though he is a large difference from the average height, people who are that tall represent a small proportion of the population. So got that? Large differences from the mean occur a small amount of times. Low probability. Rejecting null hypothesis. Given a small probability, which always accompanies a large z-score, you reject your null hypothesis. Your null hypothesis in this case is there is no difference from the mean. Let's continue. What about Maria? Maria is 5'4", or 64 inches. The average height for a woman is 62.6 inches. Aren't you glad we did the proc sort by sex now? So we have the average height for women, and the standard deviation is 2.5. She differs a small amount from the average, and that will happen a large proportion of the time. So, would you accept or reject the null hypothesis that Maria is no different than the average height for women? Think about it. I'll wait. Compute the z-score. Her z-score is 64 minus 62.6 divided by 2.5. And that comes out to 0.56. The probability of a z-score that high or larger is almost 60%. The probability is greater than 0.59 that you will get a z-score that high just by chance. So you should accept the null hypothesis. So let's compare group means, the next step in hypothesis testing. Let's start with the z-test for the mean. This is the same general idea as comparing one score to the mean. Instead of subtracting the mean from a score, you are subtracting the population mean from the mean of a group. What do you use for the denominator? The standard error of the mean, which you may remember from class, is the standard deviation divided by the square root of n. Let's do an example. I actually read this book recently, A Long Way Home, which is a really incredibly good book. I highly recommend it. And I noticed in here when this boy who was lost at 5 years old in India and ended up being raised in Australia, when he went back home, he was way enormously taller than the other people that lived there from his family. So I'm just wondering if this is a general thing. In fact, I'm wondering if people from India raised in the U.S. are taller than people in India. So to test if there's a height difference between Indian Americans and men in India, I would compare my hypothetical population I collected with the actual mean height, which I looked up, of 65 inches for men, and a standard deviation of 2.5 inches for men in India. So let's say the mean of a group of 100 men I measure is 67 inches. I'd take my sample mean, 67. I would subtract from that the population mean, 65, and divide that by the standard deviation over the square root of n. Well, the square root of 100 is 10, so it's 2.5 over 10. So the difference is 2 inches. 67 minus 65 is 2. 2.5 divided by 10 is 0.25, and that gives me a z-score of 8. A z-score of 8 occurs way less than one time in 10,000. So I would reject my null hypothesis and say that if I really did get a group mean with 100 men of 67 inches, that the mean height of people raised in the U.S. was higher. Now let's look at an independent t-test. This is the same general idea as comparing a sample mean to the population mean, but a lot of times you don't have the population mean. You just have two sample means. So you're going to subtract the mean of one group from the mean of the other group. But what do you use for the denominator? I mean, standard deviation divided by the square root of n, but what standard deviation? For which group? So the answer to that is your denominator is the pooled standard deviation. Your denominator is the pooled standard deviation multiplied by the square root of 1 over n1 plus 1 over n2. Let's look at this formula. So, first the pooled standard deviation. Basically, this is the average of the standard deviations of the two samples. Think about it for a minute. If you had, say, two groups, and one had 1,000 people in it, and the other had 50 people in it, and you were trying to get the standard deviation, you wouldn't weight the variances of those two groups equally, right? So this is basically a way of weighting the standard deviation by the number of people in the group. So you have n1 minus 1, number of people in group 1 minus 1, times the variance of group 1. Remember, the standard deviation is the square root of the variance. Plus n2, the number of people in group 2 minus 1, times the variance of group 2. You divide that by the number of group 1 plus the number of group 2 minus 2, and you take the square root of the whole thing. That is your pooled standard deviation. So it's basically an average of the standard deviations of the two groups, a weighted average, weighted by how many people were in each group. So remember, you're comparing means. So just like when we had the mean of one group, and we subtracted from that the population mean, and we divided it by the standard error of the mean, in this case, we're going to take the pooled standard deviation and multiply that by the square root of 1 over n1 plus 1 over n2. So we're getting the standard error of the difference between means. And we take the difference between the mean of group 1 and the mean of group 2. We divide that by the pooled standard deviation multiplied by the square root of 1 over the n1 plus n2. And that gives us our t-value. Now, here's an applied statistics tip. Notice that as the size in either group changes, your standard error will decrease, assuming the groups have somewhat similar standard deviations. So if you can't get more people in the treatment group, add more to the control group, and that can increase the power of your test. So let's take another look at our independent t-test example. The larger value you get here, the more likely you are to reject the null hypothesis. In other words, just like a difference from the population mean occurs less likely if it's a very large difference, the difference between two means occurs less likely if it's a large difference. Another factor in how probable the difference between means is how great the variance in the population is.